Hi, I'm Sophie Pelsmakers, and this talk is about overheating prevention, which we're finding is even more important in a warming world. This is part of the passive resilience theme, and as you know, this material has been produced by the Arc for Change project that was co-funded by the Erasmus Plus programme of the European Union. So what is building overheating? Well, building overheating in cold and temperate climates occurs mainly during summertime. But definitions of building overheating vary a lot depending on the regions. It tends to be focused on maximum temperatures that shouldn't be exceeded, but also to the duration of exceeding certain indoor temperature thresholds. For example, in Germany, building overheating is considered to occur when temperatures are between 25 and 27 degrees Celsius. In Finland, building overheating occurs when the limit of 150 hours above 27 degrees Celsius is exceeded. And in Brussels it's a bit more complicated. They consider building overheating to occur when 5% of annual hours are over 25 degrees Celsius with no more than 5 degrees Celsius difference between indoor and outdoor temperatures. On the right, you can see some recommendations for living room, office and schools to be at 25 degrees Celsius maximum as indoor temperature. But some peak temperatures might occur, for example 28 degrees Celsius, as long as they're not more than 1% of the occupied time. And then of course bedrooms and living spaces shouldn't be more than 21 degrees Celsius maximum. A peak temperature of 26 may occur when it's not more than 1% of the occupied time, but ideally for health and well-being implications, the temperatures stay below 24 degrees Celsius at night time. So what causes building overheating? Well, buildings overheat when the heat gains from the outdoors, but also the heat generated indoors, are greater than the heat losses for a prolonged period of time. And of course, the heating risk is influenced by many different factors. The first one is the outdoor environmental conditions, so how hot is it actually outside? Also the design of the building, for example, how much sunlight can actually get inside spaces and how long it remains there. Of course, also the internal production of heat, and then occupant behavior, because many measures that prevent building overheating risk rely on occupant behavior. I'll go through each of these four now, one by one. So let's start with the outdoor environmental conditions, and specifically those that contribute to increased building overheating risk. As you imagine, high temperatures outside, particularly when they're over 32 degrees Celsius, can actually really contribute to building overheating risk. And temperatures at over 41 degrees Celsius are really dangerous. But also when there's high levels of relative humidity, very little air movement, all contributes to building overheating risk. And also the urban heat island effect is an increasing risk to building overheating. The urban heat island effect is covered in different talks, but in brief, it's a phenomena where urban areas can be 2 to even 10 degrees Celsius hotter than the surrounding areas, and that's especially pronounced at nighttime. Now, how that happens is that basically in the daytime, there's a surface absorption of solar gain, but of course any other heat that is produced in cities as well, and at nighttime it is released back into the city. And then certain regions of Europe have very long summer nights, for example, Northern Europe and particularly the Nordic region and Scandinavia. And they have very low solar angles as well. So both these long summer nights, the low solar angles, means that the solar gains can enter into spaces for a very long period of time. It also means that even facades that face to the north receive low angle solar rays on late summer evenings. And that then all contributes to the building overheating risk. Specifically, in Northern Europe, spaces have been designed with cold winters in mind. So it means that we're designing them to get a lot of the solar gain coming inside spaces and then retain that heat because that's free heating in summer. The problem is that in summer, of course, when these solar rays can get into spaces, they also stay there for a longer period of time and then contribute to overheating risk. And of course, then there's also the changing climate, which further exacerbates warm summers and extreme temperatures. We've already seen that regions with currently cooler summers are experiencing much hotter summers and extreme heat waves that increase the building overheating risk. This is predicted to only increase in the future because globally we're not on track to reduce CO2 emissions to keep global heating to below 1.5 to 2 degrees Celsius. That means that we need to both mitigate but also adapt to a changing climate that is already here and will exacerbate building overheating also in the future. The other cause is that of the building design. So the design of the building can increase overheating risk in spaces because the heat transfer from the outdoor environment can contribute to overheating through, for example, the conduction of heat through the opaque building fabric, particularly if it's not very well insulated. But also, of course, the solar heat gains through the windows in summer if there is no summer solar shading. And then, of course, in summertime, hot air can come inside through the building from outdoors, for example, through ventilation. Particularly, of course, if the temperatures are hotter outside than inside, we should not be using purge ventilation. We're only then heating up the building. And then, of course, as well, if we don't use nighttime cooling to dissipate this hot air, that also then contributes to heating build-up in spaces. Let's go through some of these key principles. So, first of all, a well-insulated building fabric keeps the heat inside in winter. That's the whole idea of particularly a well-insulated fabric. But of course also in summer, if there's no solar shading or there's no ventilation strategy to stop the summer sun coming in or the hot air coming inside or being dissipated out, it also keeps that heat inside. Now, thermal mass in buildings can balance these peak temperatures, but they also cool down more slowly unless there is very good nighttime ventilation that helps dissipate that stored heat from the day at the nighttime. Particularly east and west facades are subject to these high solar gains because the angle is much lower, and they're often also more difficult to shade from this low angle solar radiation. That can in turn then result to overheating and can also cause uncomfortable glare in non-residential buildings. Of course, when there's building overheating, that in turn can then increase the likelihood of active cooling. The spaces at risk most are those that are in apartments on the top floor, especially if they're under not very well insulated roofs, and also those that have large unprotected windows facing the sun. When we undertake building retrofit, for example, to increase the insulation and reduce the heat loss in winter, it can also reduce thermal mass, particularly when we're covering the thermal mass of stone or brick walls on the inside. So when we add internal wall insulation, we can actually reduce the thermal mass capacity. That can then contribute to building overheating unless we combine that with other measures at the same time. For example, blocking the sun out through solar shading and undertaking nighttime cooling and so on. Of course, when we have small window openings, they can also block the ingress of cool air, especially at night. And this is, for example, particularly the case in the Nordic region, whereby windows are designed to be airtight, to only provide some background ventilation, and they're not designed for what we call this purge ventilation, which will be covered in another lecture, to create this cooling at nighttime. And then it means that actually there is not enough cross ventilation or just ventilation to cool down spaces in heat waves. As I mentioned before, these internal heat gains can also increase building overheating risk. So it's not just the sun coming inside, but also heat that is generated inside can contribute to overheating. That heating comes, for example, from people and their activities like cooking, but also, for example, if there's many people in a small space, they produce a lot of heat, which is then retained inside. We've also found that hot pipework that is insufficiently insulated can give off heat and can contribute to building overheating. And of course, when there's a presence of energy inefficient appliances, it means that they give off a lot of heat and then can lead to these high internal gains that they can contribute to building overheating. For example, lighting, fridges, freezers, and so on. And that brings us to occupant behavior. because many overheating prevention measures depend on occupant behavior. For example, we need to close the windows when it's warmer outside than inside, otherwise we bring hot air inside, which then, if it's well insulated, stays inside the building envelope. We then should be opening windows at night time when it's cooler to bring that cooler air inside and to dissipate that heat from the thermal mass to the outside again. And we might have to use movable shading, for example blinds, perhaps even active systems like fans, cooling and mechanical ventilation as well, during the daytime. But people might not actually undertake these actions, and that is often because they actually don't know how to, they don't have the information or knowledge, but also, of course, opening windows has implications for security and safety, and also, of course, acoustic issues at night time in inner city areas as well. So who is most affected? Well, hot temperatures unfortunately also elevate ozone concentrations and other pollutants in the air. That then further exacerbates asthma and other respiratory illnesses, so vulnerable people are affected even more during heat waves. Then older people and other people with underlying health conditions might not sense hot temperatures very well, and so they may be unaware how hot it really is, and then it can exacerbate health conditions further, for example, cardiovascular issues. Also, older people and the very young might not be able to undertake adaptive measures during hot weather. So, for example, it might not be easy for them to adjust clothing or to open and close windows and blinds, maybe even to move to cooler zones inside the space or in the building. And so it means that they're also then more vulnerable to heat as well. And of course, we have a combination of and a clashing of different crises. So the climate and the aging crisis are combining. So we have a changing climate with hotter summers that are predicted at the same time that there's also an increase of an aging population in most countries around the world, and especially in Europe as well. So it means that it will be even more vulnerable as actually the temperatures will become more extreme. So what are some of the consequences of overheating? Let's look at health implications. So building overheating can cause thermal discomfort, for example, also prevents us from sleeping, which then affects health and productivity. For example, when room temperatures increase by more than 3 degrees Celsius, there is actually a 10 to 15% reduction in productivity the next day. Building overheating can also cause thermal stresses, and that means when the body's core temperature rises too much, the heart rate increases, and that can even lead to mortality. What we do need to keep in mind that at present in Europe, cold-related mortality is still a bigger problem than heat-related mortality. Of course, that may change towards the later part of this century. Of course, all of this also has social welfare implications. When there are premature deaths, increased hospitalizations, and increased emergency room visits, all of that affects healthcare provision and the pressure on healthcare and society. What is interesting, though, is that in hotter climates, the heat-related mortality and the issues occurring related to health occur at higher outdoor temperatures than in cold and temperate Europe. And that can be explained because people in hotter climates have been able to already adapt physiologically and behaviorally. And of course, they also tend to live and occupy more appropriate building designs and infrastructures that are specifically designed for hotter climates. And that's why it's so important that we learn from those hotter climates and include some of those key adaptive measures across all of Europe as well, keeping in mind the current heat waves already, and of course the future predictions of our hotter climate as well and extreme temperatures. Let's look at some of the energy implications of building overheating. Now, building overheating can lead to an increased use of energy and then, of course, also associated carbon emissions. And that's because, of course, if people cannot stay comfortable, they may then install active systems to provide active cooling. That then increases the energy use and the carbon emissions, directly contributing, of course, to the climate emergency. but also it further exacerbates and contributes to an increased urban heat island effect because it pushes warm exhaust air from inside to outside, increasing the urban heat island effect even further. Of course, another implication is also when we rely on active systems, we also rely on a secure energy supply. If that power supply fails, buildings may actually become unsafe to occupy. So using active systems also creates energy dependency, and that is why it is so important that we consider passive measures first to mitigate building overheating risk. Other consequences of building overheating are injustices and inequalities that may increase. For example, the people that can afford building adaptations can protect their comfort and well-being because they can afford to install the shade, to mechanically ventilate, to buy active cooling units, and to also pay for the ongoing energy costs associated with them as well. But those that cannot afford the installation or the running costs of these systems, they will suffer more. They will suffer more from summertime energy poverty and, of course, will have more of these health-related implications as well. So it really creates these injustices. There's actually already evidence that less well-off households are already at higher risk of overheating, and it further exacerbates injustices. For example, they might live in warmer neighborhoods, therefore they might sleep less well, they're less productive at work, that might affect their earnings, or for example, children studying at school. Many people also live already in smaller overcrowded units, so all of this already is exacerbating these injustices. So we need to be very aware when we undertake certain measures to mitigate building overheating, that this is done in a socially just way. So what are some of these overheating mitigation or prevention strategies? As we just mentioned, overheating is caused by outdoor environmental conditions, the design of the building, the internal production of heat, and also occupant behavior. So what's really important that we need to do first, and most importantly, is that we remove or reduce all of these causes of overheating where we can. And only after we've done that, so after we've taken all of the causes of overheating away, then we must prioritize overheating prevention strategies that reduce the energy need for cooling. And we need to do that through passive cooling strategies first before we even consider anything else. So some of these key passive cooling strategies include green and blue infrastructure at the macro, meso and micro scale that then actually also benefits biodiversity and carbon reduction. And this is discussed in more detail in another lecture. We also need to include social infrastructure at different scales. And what that means is that neighbours will look after each other during heat waves. They care for each other. It also means the provision of safe, cool zones in buildings or neighbourhoods. And again, that is covered in another lecture in more detail. And then, of course, we need to reduce the internal heat gains in the building and implementing simple, easy-to-use solutions related to occupant behavior. And we then need to make sure that the building is designed that reduces the need for active cooling. And all of this is covered in different lectures. Some key snapshot ideas, what we can already do at the building scale that reduces the need for active cooling measures. So for example, things that you should include in your project are light colored and reflective surfaces to reduce the urban heat island effect. Careful building form and orientation, so only capture the sun where it is needed. Careful location and design of windows as well. Providing an efficient fabric so that in winter time it can actually keep the heat in, but that also at summertime the heat can be dissipated out. And of course, we also should prevent the sun coming in the first place and provide summer solar shading without blocking it at winter time. And then through purge ventilation and night cooling, especially when we combine it with thermal mass, we can also make sure that we can passively cool the building at night time. But all of this is discussed in more detail in another lecture. So in summary, building overheating is an increased risk in a changing climate. It is influenced by outdoor environmental conditions, the design of the building, the internal production of heat, and occupant behaviour. Overheating affects the health and well-being of people, especially older and vulnerable people, and it can lead to increased injustices and even cause increased mortality. Key passive cooling strategies that you always should include in your project are, first of all, ensuring that all causes and sources of overheating are tackled first and those risks are minimized. Then you should include green and blue infrastructure at different scales in your project. And also, of course, social infrastructure and provision of cool zones. And in your project, you should make sure that all internal heat gains are reduced and that you understand occupant behavior and design with that in mind. And then you should design your building that reduces the need for any kind of cooling. If you want to know more, you can look at the video description for further readings and examples. And as you know, there's much more material available on the platform, which has been produced as part of the Arc for Change project. Thank you very much.